Chapter 3, Exercise 11. Prove the following version for functions of the extensionality principle. Assume that f and g are functions. The domain of f is equal to the domain of g, and f of x is equal to g of x for all x in the common domain. Then f is equal to g. Okay, so yeah, let's just do this. And what I'm going to do is just treat these as if they were sets, and then try to use the information that is given to show that they're both subsets of each other. So let's suppose and recall that, actually before that, recall that functions are single-valued relations under our definitions. And what this means is that by single-valued, I mean that every x in the domain has exactly one corresponding y, such that that pair is in the function. That is, if you take f of x and that is equal to y, then that is the only y for which f of x is equal to that. It can be equal to two different things. Just your basic notion of whatever a function is, that is what I'm saying here. And relations is that, again, a relation is a set of ordered pairs. So every ordered pair is single-valued. That is just a useful fact to keep in mind in general when thinking about functions. Okay, so now suppose x comma y is in f. Right. Then x is going to be in the domain of f. I hope that by this point I don't have to justify that too much. If not, please watch my previous videos. I go over why exactly this implies this several times. Okay, so x is going to be in the domain of f. And since the domain of f is equal to the domain of g, x has to be in the domain of g as well. Okay, cool. Now, given that x is in the domain of g, there must exist some y in the union of g such that x comma y is an element of g. Or, in other words, there exists some y such that g of x is equal to y. And you know what? Let's call this y g, because if we're treating this in all generality, then it doesn't have to be the same. This is just like some arbitrary y that is in g that satisfies this relation, right? But since f of x is equal to y, and we assumed that for all x in the common domain, which I'm going to define as domain f intersect domain g, and we assume that f of x is equal to g of x, then y sub g is equal to our original y. This means that x comma y, our original x comma y, has to be in our function g. Therefore, f must be a subset of g. And the proof for the other way around is exactly the same. You just swap out g for f. So let's do it again so we get some good practice. Now suppose x comma y is in G. Just as a quick aside, I use this definition because I like to be reminded that I am working with sets. Otherwise, my previous knowledge of functions can get somewhat in the way, I'd say, of what I'm doing, and I try to avoid that as much as possible. You can also say that if x comma y is in G, this is equivalent to saying that g of x is equal to y, which is equivalent to saying x g y. Just so you keep that in mind. If I ever use those other notations for convenience, I will. I'll probably remind you of this fact, but otherwise, it's just something you should keep in mind. Okay. Then x has to be in the domain of G, which, as we stated earlier, implies that x is in the domain of f, since these are equal by assumption. So there exists some y sub f in the union of f such that x is in, the pair x comma y sub f is in f. But if x comma y sub f is in f, then f of x is equal to y sub f, which should be equal to g of x, which should be equal to just our original y. Thus, y is equal to y sub f. So this means that our original x comma y has to be in G. No, in f. And thus, G is a subset of f. And we conclude that f and G are the exact same sets. That is, the functions are equal. So, more grounded in math, which is probably most of our background, this is just saying that if the functions have the same domain, and if the functions have the same value at every x in the domain, then the functions are the same. I think it's a very reasonable thing to say, and it is also a theorem of set theory, so there you have it. Our intuition matches the reality of mathematics, which is always a nice thing to know. Right, so I hope this was helpful, and I will see you in the next video. Bye-bye.